Okay, hello. Today we will look at, or now we will look at pressure and buoyancy. And let's go. If you recognize the music, that would be great. It never fails to give my spirit a certain form of buoyancy. Alright, so we're going to start off by defining pressure. So some of you might be feeling a bit pressured right now because exam coming soon now. Okay, so this one is just a recap from your younger days. Pressure is defined as force per unit area. Alright, so this is a scalar quantity. Unit here is Pascal, PA. Don't get so attached to this unit or Newton meter -2. Sometimes it can be measured in other units as well. We will look at some examples here. Okay, so when we measure pressure, right, you think that there are a few equations. Actually, it's the same equation. Now, pressure here, when we want to look at liquid, fluid, or gas, okay, we will use the force, which is the weight of the fluid. A lot of times the force here is weight, so we'll take mg over A. And your density here, since is equal to m over v, so you get m is equal to v times rho. But also at the same time, oftentimes v is area times height. So I can put area times height times rho. That would be your mass. So I can then substitute into pressure, no? Ah rho times g divided by A and cancel off the A. Ta-da! So pressure, being equal to H rho G is actually a direct consequence from P is equal to F over A. We tend to use this a lot when it comes to fluid or gas, and when we measure, we use barometer or manometer or U-tube. I also noticed I didn't include this chapter in your test too. Never mind. Alright, so we also need to talk about Archimedes principle or your buoyant force. Again, discussed before Liao, so not going to emphasize too much. But Archimedes principle here, whenever they ask you what cause of Archimedes principle, this is pressure difference. Okay, so let's now just jump to an example first. Here you can see a block submerged vertically in a liquid. We're going to assume that all blocks are at the same depth lah. This is the water level. Okay, so we know that the deeper you go, the higher the water pressure will be because you have more water on top of you pressing down against you. Okay, and from Pascal principle, pressure should be acted on all directions. That's why B is out. The side no pressure meh? Not supposed to be, right? The side will always have pressure. Okay, so D is also out because you look at the pressure, or the pressure is the same at the side. Where can? So cannot lah. So the second part, right, is to compare the pressure at the same point. You will notice that A will have the same height at that point that I crossed, so they should have the same pressure. Whereas if you look at C, right, very weird. Same height but very different pressure. Okay, so we are relating force to pressure, and you notice that there's a pressure difference between the top and bottom. On the top, there's less water, so less force law. Down there would be high pressure because there's more water on top of it, so more force. Okay, so there will be a net force from the high pressure pressing up on the low pressure. That would be your buoyant force. Hence the pressure difference. So the proof for this is fast enough, so I can do it for you in a few minutes. But let's say you have an object that is submerged inside water, okay? And because it is submerged inside water, what happens now is that there's a pressure difference from the top of your and the bottom. Okay, so let's say H1 from the top of the cylinder, H2 at the bottom of the cylinder, and then you have a fluid with density rho. So you know that this pressure or this net force buoyant force that helps you float the object is due to the pressure difference between P1 and P2. So, and you know pressure is force over area. So I can take P2 minus P1, which is the pressure difference, times area is equal to your net force. So I'll take H2 rho g minus H1 rho g times A is equal to your net force. This is your buoyant force or your upthrust. I'm just going to call it FB. Facebook. So simplify a bit law, H2 minus H1 times A rho g is equal to FB. And I don't know whether you notice or not, but H2 and H1 is equal to delta H, which is the height of the object that you submerge. And then if you multiply by A, it's actually the volume. Okay, so I'll write that down for you. Delta H times A is actually the volume of the actual object that you submerge in the liquid. Okay, and if you remember not too long ago, V times rho is actually mass. So FB is equal to V rho G is a useful equation to use. Bearing in mind that the density here is the density of the liquid lah, okay? But also mass is equal to V rho, right? So I can put FB is equal to mg. So do not confuse this with Archimedes principle. Archimedes principle is the blue color statement. Buoyant force is weight of the fluid displaced by an object. Okay? But it's due to the pressure difference. Okay, let's try an example. Okay, we're going to do a few conceptual examples first. Here you have a bunch of blocks, and then you are asked which two blocks exert the same pressure on the ground. So this one very confusion one lor, because it depends on so many factors. So I think the first order of business is actually to calculate the volume, because they all have different density. So the volume will be AH, 2AH, A is being the surface area, 4AH and AH. Okay, I'm looking for the volume. And I know P is pressure over area, and the force is mg. So I can substitute M is equal to rho V into the equation. And I think I'll just leave it at that lah. This is your pressure, rho Vg divided by A. So everyone is density rho except T. T is 2 rho. So now I'm going to write down pressure for every single one. So you have the density rho times the volume AH times G over A. So this one will be actually H rho G. Okay lor. Now pressure now here will be equal to rho times 2AH over G times G divided by 2A. So the pressure is the same. Okay, what about this one? Well, this one, I would take density times 2AH times G divided by A. So this is actually 2H rho G. Not the same. Okay, and this one would be rho 4AH G. Actually, there's a slight mistake here. I should divide by 2A. I will correct it later. So this one density is doubled. A times H G divided by A. I'm just substituting rho V and G, that's all. So this is 2H rho G. You will notice that P and Q is the same. Unfortunately, 没有答案, no answer. You have 2H rho G for R and T. No answer. That is when I noticed I made a mistake, because the surface area of block S is actually 2A. So I paused for a while in confusion. Then this is 2A. So this would be 2H rho G. So R, S, T are all the same. So you find lah which one got R, S, and T. So the answer is D lor. Okay. So we're just substituting all the rho and all the V and all the A and simplifying and comparing the terms. Okay, now this one is a sphere underwater. So S and Q is the same height. So the forces acting on S and Q will be the same. pressure at S is equal to pressure at Q, so the force at S will be equal to the force at Q. How about P and R? P is at a higher position, so the pressure at P would be less than the pressure at R. So the force at P will be less than R. Okay. This one, you see a submarine. What causes the upthrust? Actually, you don't even need to read, You just look for pressure difference. Another word for upthrust is buoyancy or buoyant force. Pressure difference. Okay lah, D. Not saying that A, B, C are wrong statements. It doesn't matter whether the statement is correct or wrong. Like for example, A is a correct statement. Air is less dense than water, but that does not cause upthrust. Okay, seawater exert a greater upward force than the submarine. If the submarine is stationary, right, the seawater is equal to mg. Okay, and the submarine displaces its own volume. That one is also correct statement, doesn't explain. So now you have a bunch of thingy-majigs with different density, and then you're asked to compare the upthrust. So all the density different. How? Well, my friends, this density is not the density of the object, it's the density of the water, remember? So the density of the water is constant, G is constant, volume of the water displaced based on the shape is also constant, so they're all the same. See, they're quite tricky. So right now you have this, they're all in equilibrium, and you're asked to compare the tension in position P, Q, R, and S. So to compare this, you can see generally when at this position, T at S will be equal to mg because there's no buoyant force, not yet submerged. R is partially submerged. So TR will be equal to TR plus buoyant force will work together to support mg. So TR is less than TS lah, logically. TP plus new buoyant force. So this new buoyant force is bigger than the old buoyant force lah, because more of the object Q is submerged. P and Q have the same buoyant force because it is equally submerged. It's the same volume of water displaced or the same pressure difference. Okay, so TP is actually equal to TQ. So you check all the statement one by one. Okay, the tension in T is the same because of the difference in pressure. No lah. So B is wrong because tension in T is less than tension in P. Okay, I'm just going to pause this a while so we can read without distraction. So if you look at A, right, okay, at P and Q, the tension in the chord is the same, okay, because the difference in pressure from here to here and here to here is the same. The difference in pressure is only dependent on the difference in height. So P and Q are identical objects, have identical height. Alright, so A is correct. B, at Q, P, tension in the chord is less than P. Cannot, tension is the same. Okay, so at Q, the tension is the same as P. At R, tension should be more because the buoyant force is less. You need more tension to support the weight. Okay, now the last one, at S, tension T is greater than P. Tension T is greater than P, but it's not because of atmospheric pressure. It's because of the absence of buoyant force. There's no buoyant force. That's why the tension have to do all the work to support the weight. And this kind of atmospheric pressure difference is negligible for small volume lah, because the air got small density. Okay, there's less density in air. By the way, right, and it's about less than 1,000 times the density of water. So if you want the atmospheric pressure difference to be significant, my friends, we need a huge hot air balloon. Okay, so like right now, here you see an air bubble in the water tank rising at constant velocity. Okay, and you're asked to identify the force. So this is an air bubble, so the weight is very small. The Y is definitely the weight. The only thing that can push it up is the upthrust or the buoyant force. Okay, so Y must be the weight, and X must be the upthrust. And this thing is in equilibrium, so X is equal to Y plus Z. constant velocity ma. Okay. All right. Now we're going to look at this kind of pressure measuring device. In this case, right, you have a gas trapped on one end and the other end is open. Okay. So there's an important concept in solving all these questions. Same height, same pressure. So let's say at one end, this is the pressure of the gas pressing down on the water. And at this end here, let's say point A, the pressure of gas will be equal to the pressure at point A because it is at the same height. Alright, so pressure at gas will be atmospheric pressure because that end is A is open, and plus 5 meter of vertical distance of water. Okay, so 5 meter water can be converted to Pascal just by substituting 5 and density of water times 9.81. They ask you to use 10 here. Atmospheric pressure is 1 times 10 to the power of 5. Okay, so H rho G can be converted to, 5 meter water can be converted to Pascal. Just put 5 and density of water. Why did I circle C? That's B. The answer is C. See lah, write 1.5, go and circle B. Late liao, that's why. Okay, so now we have a rectangular block. Then you are asked to find the difference in pressure. You just take the difference in height lah. 0.2 meter times the density of seawater times 9.81. By the way, the answer of the previous question, the one that looked like a straw, the answer is C. I circled wrongly. And I cannot uncircle it because I am overlaying the video with my voice and my face. Unless I start all over again. No time. I think the computer will crash. Alright, so anyway, after that rant, you can see the pressure is 2.16 or 2.2. Alright, now you have two bulbs, X and Y, okay, air of different pressure respectively. So they're asking you which pair of values is possible. Well, my friends, again, same height, same pressure lah, okay. Because you see on both sides they have the same gas, so they should have the same pressure. So H2 over H1 will be equal to Py over Px. So the ratio should be 1 to 2 lah. So there's only one ratio that is 1 to 2, which is A. Okay. So formula for hydrostatic pressure, which equation or principle is used to derive? Why got GPE one? You remember my derivation, right? I use A. Right, density is mass over volume to cancel off the A. Alright. Oh, look at this. I think Mr. Nagapan got discussed this question with you lah, but I just put this here lah as a placeholder. This YouTube, by the way, is known as manometer, not the one that we subscribe, click like and bell buttons. Not that one. Okay, anyway, again, just to emphasize the concept, from P is equal to H rho G, same height, same density, will have the same pressure. So I'm going to take these 2 points because they are at the same height, so they should have the same pressure because they are inside the same liquid. Okay, so now open end, so got atmosphere. Just now the previous one with the yellow gases, close end, no atmosphere, okay? So at point A, you have atmosphere pressing down plus 2x length of whatever P is. Okay, like 2 meter water, this is 2x of P. At point B, you have atmosphere and x length of liquid Q, whatever liquid Q is lah. So we will cancel off the atmospheric pressure and you will get 2x times density of P times G is equal to x times density of Q times G. Again, using H rho G. So then you can get the ratio of rho P over rho Q as 1 over 2. Basically, Q is more dense lah. So like you look at this one end, closed, no atmosphere. The other end open, got atmosphere. Okay, open end has atmosphere, closed end has no atmosphere. Okay, so actually you can use logic lah. If A and B pressure the same, surely Q is more dense. Okay, look at this W tube, W, more like triple U. Okay, so they're asking you what are the possible combinations of X and Y. So I think the only thing I can do is same height, same pressure lah. So A is equal to B. Okay, pressure at B is pressure of gas P, and then what is pressing down on A is atmosphere plus X length of mercury. Okay, point C and D would also have the same pressure. So then, point C, what is pressing down on point C? Gas P lo. What is pressing down on point D? Atmosphere plus 50 minus Y cm. Or mm, sorry. So I got two equations. DK what to do? Equate them lo. Okay? It's a bit the same like the yellow gas lah. Alright, so I'm going to equate both equations, and ta-da! Thankfully both sides are open. Okay, so can cancel off the atmosphere, and then you get 50 minus Y rho G is equal to X rho G, because they are all mercury ma. So from here I get X plus Y must be 50. Ta-da! Okay, since it's MCQ, let's do process of elimination. X plus Y must be 50. Wow, this one wrong, this one wrong. Oh. So you kind of like have only two more options left, which is either B or C. How? Well, you know in maths, right, there's this method called trial and error. So this is what we're going to do. We are going to trial and error. Sorry, my laptop went to bed. It's 1 AM. We should all go to bed. Okay, anyway, where was I? We're going to trial and error, okay? Because there's no way for you to tell how. There are too many unknowns. Please don't hurt your head. So I'm going to substitute maybe option B first. So option B, right, X is equal to 20 and Y is equal to 30. So I'm going to sub into equation 1, okay, where pressure P is the atmospheric pressure plus 20. Because 50 minus 30 is 20. 50 minus Y ma. Okay, and equation 2, atmospheric pressure would be P times 20. Okay. Of course, these two have to be the same line. If not, you do wrong liao. Okay. So I think at this point in time, you might know what to do. But again, I just want to compare the options. So I'll do both. Okay. So for this one, X is 30, Y is 20. So again, P is either equal to atmosphere plus 50 minus 20, which is 30, or PATM is equal to PX, plus PX, which is P30. Now in the question, you are given that the pressure of the atmospheric pressure is 760 mm. So let's try and sub and see. Okay, so this P20 is also millimeter mercury. Okay, and then if you check the other one, this is also millimeter mercury. One is 780, one is 790. 810 is out of the question, so your answer is B. Try and error lo. More straightforward already. Okay, and finally we arrive at this thing. Don't care about the area lah. We are still doing the same thing. There's some trapped air, so one end is closed and the other end is open. You are given the density of mercury. And then there's also a piston that is applying pressure downwards. Okay, same height, same pressure, A equal B. I think you get the point already. So many questions, all the same. Okay, so let's consider what is pressing down on A. What is pressing down on your soul? Okay, you got your atmosphere and the pressure due to the piston. Alright, what about B? B, there is some trapped air. Okay, so I'm going to put pressure of air plus HCm of mercury. So we can put millimeter mercury like the previous question. Okay, you can keep it in millimeter mercury if everyone is millimeter mercury, but unfortunately, no lah. You got Pascal for atmosphere, and then the pressure due to the piston, you can use force per unit area, mg over A. Pressure of air is given, and then this pressure of your HCm mercury, you have to keep it there first law. So basically, you're trying to find the pressure exerted by the mercury column. Okay, we can now substitute. Mg is 5 kg, so don't forget to multiply by 9.81 divided by the area. Okay, so this is HCm mercury. Okay, so I'm going to press the calculator to see what I get on the left side. Okay, and based on what I got on the left side, this is Pascal. To convert my cm mercury to Pascal, I'm just going to use H rho g lah. Okay, so H height of 13600 Mercury will give me this much pressure. Find H. Okay, so this will be 1.12 meter. This is 112 cm, so take the closest answer. So my friends, the moral of the story is that pressure is force per unit area. Okay, if it's Pascal, we can take mg over A. But sometimes we use H rho g when you want to convert to millimeter mercury lah, centimeter mercury lah, meter water lah. Okay, so the millimeter is for H, cm is for H, m is for H, and the density will take the density of your whatever liquid you're talking about. But make sure you convert everybody to SI first. And the important concept to solve all the questions, same depth or same height, you will have the same pressure. Okay, and if different depth, then you have a pressure difference. The pressure difference causes your buoyant force or your upthrust. Okay, and we can calculate upthrust using V rho g. Okay, and upthrust is also equal to the weight of the water displaced. So this is the final question for the video. You see there's a spring attached on one end on a fixed point, and we are going to let go. Okay, the cube is initially held so that the spring has zero extension, and then the cube is released and sink into water as the spring extends. The cube reaches equilibrium when the base is 7 cm below the water surface. You're given the density. Calculate the difference in pressure exerted by the water on the top face and the bottom face. So again, you're asked to find pressure difference, or delta P. Okay, so you can just take the difference in height across the cube, delta H, multiply by density and the height, and the density of water. I mean, it's 5.1 cm lah. You gotta make sure everybody is SI. If not, your final unit cannot be in Pascal. Okay? I'm not sure if the glare of the laptop prevents you from looking at my eyes. Let me turn it down. Okay, I shall bring it down a few notches. Alright, there we go, more comfortable for everyone. So use your answer in A to show that the upthrust on the cable is 1.3. So once again, upthrust, delta P, is due to the pressure difference. So F is equal to delta P times A. Okay, because P is equal to F over A ma. So we're going to put 500 here, and then the area will be just 5.1. Oh, don't forget to convert to meter, because all the unit in the equation is SI. Look, if you don't know whether you're supposed to convert or not, then you just convert lah, until you have a good intuition whether you need to convert or not. Alright, so I think this one you get 1.33. 1.3, 2.7. I think it's 1.3. Alright, so this is proven. Did I forget to speed up this part of the video? Feels extra slow. Anyway, calculate the force exerted on the spring by the cube when it is in equilibrium in the water. Okay, time to draw a free body diagram to show the forces acting on the object. So far, before we do this, right, maybe I shall speed up the video a bit. I think it's worth remembering that we learned 4 types of forces. Tension, which exists because there's a spring here. Weight, which always exists as long as you are in the Earth's gravitational field. Tension, weight. Normal force don't have, there's no surface to touch. Again, we omit the water as a surface, okay? But what is actually, so there's tension, there's weight, we ignore normal, we ignore friction because it's not moving. The 5th one, which will only happen if you're partially submerged, is actually buoyant force. So in this case, you have buoyant force. And we are going to draw the weight, okay? So you can see there's a 4 Newton acting down. And also at the same time, there's a buoyant force pushing it up by 1.3 Newton. And you will have a spring with tension T. So this tension T, is actually 4 minus 1.3 Newton. Okay, it is 4 minus 1.3 because what we are doing here is we are asking ourselves, actually the tension really need 4 man? No need lah. Buoyant help it by 1.3. Okay, so 4 minus 1.3 is 2.7. Just write that in. And the next part, spring obeys Hooke's law and have the spring constant. Determine the initial height above the water surface of the base of the cube before it was released. So the actual tension in the spring is actually just 2.7. So if you use F is equal to kx, excuse me, you can substitute 2.7 and 30 and you will find x as 0.09 meter or 9 cm. Okay, so because this is 9 cm, if you go back here, now I'm going to demarcate or indicate where the lengths are. Okay, because you want to know what is the distance of the diagram on the left from the water level, right? Because the diagram on the left, the spring has 0 extension. So I'm going to draw this part, and you know that the spring will extend by 9 cm. So 9 cm is where the final position of the block is. Okay, so here to here is 9 cm. Alright, because no extension and then finally extended by 9 cm due to the 2.7 Newton. So we use logic law. This must be 2 cm not drawn to scale if there to there is 9 cm. So then the height above the surface will be (9 minus 7), which is 2 cm. Okay, and finally now the cube in the water is released from the spring. Determine the initial acceleration of the cube. So now we're going to need to draw some resultant forces. There's 4 Newton acting downwards. There's a buoyant force of 1.3, and you release the spring, tension will go away. So we're going to use net force is equal to ma all over again. Since the speed is very small, we are going to ignore water resistance or drag force. So you get 4 minus 1.3, and then you substitute the mass of the block. Mass is 4 Newton divided by 9.81. Don't make that careless mistake. And finally, you get your acceleration at 6.6. So at the last part, you are required to describe and explain the variation on the acceleration of the cube as it sinks in the water. So when the cube is sinking into the water, right, what will happen here is that it will travel faster and faster. So the speed increases. And what happens to drag or water resistance when the speed increases? Well, the viscous drag will increase. Okay, or you can just say drag force or water resistance on the cube increases. So if the viscous drag increases, then the viscous drag is the same direction as the buoyant force. Okay, it goes against motion. So because the viscous drag will increase, this will increase until it is equal so let's say this is the drag. Drag force will increase until equilibrium. So when does equilibrium happen? When d plus 1.3 is equal to 4 Newton, up force equal to down force. So when d takes over from tension, equal to 2.7 Newton. Then what happens is that it will stay at 2.7. Hence the acceleration decreases until 0. Okay? So your net force here is actually 4 minus 1.3 minus d. Initially d is 0. And then when you fall faster and faster, d will increase. So your net force, when d increase, net force will decrease. Okay? And when net force decrease, acceleration decreases. Alright? Now when acceleration decreases, what you expect is it would decrease all the way. I mean, the speed will still increase. Okay? But as time passes, the drag force increase until it is equal to 2.7 Newton. Then your net force is 0, A is 0. This is your terminal velocity, and it will maintain this speed for a while. So that is all the time, or all that we will talk about today. So in the meantime, I will see you in the next video. whatever revision video that will be up next. Alright, take care then. See you later. Bye bye.